Okay. Thanks, Charlie, and hi, everybody. It's nice to see you virtually. I hope we can again see each other really in person someday soon. But in the meantime, Charlie invited me to talk to the class about the idea of energy efficiency as a resource, and in particular, some of the aspects of how the Northwest has assumed a leadership role in developing that resource. So as Charlie said, I'm the director of the Institute for Energy Studies. I'll end the talk today with a little bit of a commercial for the Institute and our degrees and some of our courses. But just as a preview of that, we have energy degrees that are interdisciplinary in both the BS flavor, the Energy Science and Technology degree, and a BA in Energy Policy and Management. We also have minors, and we have energy concentrations in both business and engineering. And what's, I think, special about the Institute for Energy Studies and our program is that it really arose back more than 10 years ago, before my time, out of interest from students. And it was founded by Professor Andy Bunn in environmental sciences, who is teaching courses about climate change and pollution, and getting questions like, wow, we're learning about all these problems, and it's kind of depressing, man. Do we also work on the solutions? And he thought about it and said, well, you have to learn about energy, because that's where the solutions to the nexus of most of these problems lies. And he was right. And he and other colleagues at the time went about developing the Institute based on that motivation and that aspiration. And they assembled a really great group of advisors from the energy industry and government and academia and nonprofit groups all across the Northwest. And we've gradually built up a program now with those majors and minors and concentrations that I talked about, which you can see in the catalog. And I will return to in a little bit more detail if we have time at the end after talking about energy efficiency. So that's the history of the Institute. My history in energy goes back, as Charlie said, unfortunately, to a very ancient past, back in the 70s, when there were, for the first time, the idea and the problems of energy kind of arose in the public consciousness, mostly with a concern of, are we going to run out of the resource? Is there going to be enough oil to fuel our cars into the future? Are we going to have to wait in line for gasoline, as we did during a couple episodes during those days? And that was when we first started talking about energy as a topic. And Elvis met the president also. And at that time, there was kind of a conventional wisdom that we just had to go find more resources and find more oil and suffer whatever pollution arose from those resources. But there was a countercurrent of thought led by folks like my colleague at Rocky Mountain Institute, Amory Lovins, the great physicist Art Rosenfeld, the great lawyer Ralph Cavanagh, who's still very active, and a few political leaders, including Governor Jerry Brown in his first stint as California governor, and the president at the time, Jimmy Carter, got the idea that energy efficiency could also be a resource alongside the energy commodity resources that we typically think of. And let me explain in a minute what I think about that, or how I would define that. But I also want to point out that the debate has changed since that time. And over the course of my career, we've kind of stopped worrying so much about running out of the resource and become much more concerned about the byproducts of using those fossil fuel resources, specifically the threat of climate change. And we've begun to see, of course, already direct impacts of climate change from some of the extreme weather, melting polar ice, et cetera. And at the same time, the problem has transferred, I think, probably in a helpful way, from being seen as like an environmental ecological problem that's about like polar bears as the symbol, to one of salvaging our future and that of our children and grandchildren, and having a symbolic person like Greta Thunberg in Sweden, who has become such an iconic symbol as a youth spokesperson for combating the threat of climate change, I think is actually a helpful thing, because it's a human problem that everyone can embrace, not just a problem for those who are environmentally concerned. So let me get back to this idea of energy efficiency as a resource, because back in the 70s, when Amory and others came up with it, it was pretty heretical, and it's still not easy for some people to grasp, but it really is a pretty straightforward idea. Back in the bad old days, when we talked about energy systems, we had an energy chain, sort of like the one shown on the diagram here, where we'd have some primary resource, and we'd extract it from the earth, and we'd convert it with some technology and create a sellable energy commodity like gasoline or electric energy that we could sell. And the challenge at that time was keeping up with exponentially growing demand as the economy grew. And the problem was how to find enough of the stuff, and then how to mitigate the inevitable economic, environmental, and security problems that arose from using ever more of those commodities. And the challenge that Amory introduced, and the opportunity that we have harnessed from this idea ever since, is to look more fully at the chain of energy flows and energy technologies as we go from that initial production of the energy commodity through to the actual use of what we're trying to get, which is things like miles traveled down the road, or illuminating our workspace, or maybe heating our house, or running a data center. And what we find is that in between that final energy use, or maybe call it energy service, and the commodity that we were paying for, and of course polluting the planet with, there's a whole range of technologies that had been pretty much overlooked in terms of their potential to use that energy and deliver those services with far greater efficiency. That is to say, more of the service and less of the energy input, which kind of sounds like a win-win proposition when you think about it. And that's indeed the way we've pursued the idea of energy efficiency as a resource ever since. So again, the idea is to get more of the service that we want, like warm showers or cold beer, or the opposite if you're English. But either way, it's the service that we're after, and we're trying to do that with ever less energy input in terms of the commodity that we're using. And of course, that plays directly into any kind of serious strategy about decarbonization of the energy economy and transitioning from a fossil-based to a clean energy-based economy. And I talk about the three pillars of energy system decarbonization. Charlie, I don't know if you've been posing the problem in that way, but it's a fairly common perspective on the challenge of reducing CO2 emissions from the energy economy. And it starts with continued steady and aggressive improvements in energy efficiency. And then along with that, decarbonizing our electricity supply, that is shifting from fossil ever more towards renewable resources, potentially even to 100% renewable sources. And then at the same time, recognizing that some of today's energy uses that directly burn fossil fuels, like running vehicles and heating buildings, could be made more efficient. They could use cleaner fuels, but they could also be converted to electricity, which in the past didn't sound like a very attractive proposition. But now with the electricity supply being steadily decarbonized, potentially to near zero, electrification becomes a really key strategy and kind of the third main pillar of the strategy of decarbonization. And I'll talk a little bit about that later in regard to how it's complementary to a strategy of advancing energy efficiency as a resource. So those are the three pillars: efficiency, decarbonized electricity, and electrification. So as an example of how we might think of energy efficiency as a resource, here's a little article from the business press a few years ago that I picked up that talked about how in Japan, in the aftermath of the Fukushima nuclear disaster back in 2011, one action that was taken was to promote the use of LED, light emitting diode, that is highly efficient, energy efficient lighting technology to replace conventional light bulbs that were obviously wasting electricity. And in this one program, it explained that they had stimulated customers to replace 73 million light bulbs with LEDs. And that was meant to be one way of making up for the electricity shortages that had arisen because of the shutdown of nuclear plants. And so we can ask ourselves, well, wait a minute, you're talking about a light bulb. How can a light bulb have any influence over the amount of power produced by a nuclear power plant, for example? Well, to get into these kind of numbers, we have to be kind of data nerds, okay? So, that's a good reason why someone like Charlie teaches this class, right? I mean, we're all kind of the tribe of data nerds when we talk about energy. And so we look for resources like some of the government energy statistics and utility reports, for example, that show us how much and where we use energy. And so we might get charts like this. These two pie charts show us how much energy was used. I mean, this is a few years back, but they're still probably reasonably representative. In buildings, this is residential buildings, that is houses and apartments on the left, commercial buildings like offices and hotels and college campuses, hospitals and so forth on the right. And the pie chart just shows us what we use the energy for. Now, so that's the service, right? That's the cold beer and the warm shower, to figure out that if that's where we're using energy, then that's where we can potentially save energy, because that's where the more efficient technology could have an impact. And the bigger slices of that pie indicate more potential than the smaller ones, for example. So we take that approach to analyzing our light bulb example, let's say. How big is that LED lamp replacement program in Japan? Just as a simple order of magnitude example of quantifying energy efficiency as a resource. Can it in some way actually compare to a nuclear power plant? So we take those 73 million LED lamps. Each one of them saves on average about 50 watts. Okay, that's the unit of power that you're using when you turn on a conventional lamp compared to the LED. And if we make that calculation, 73 million times 50 watts, and convert from watts to megawatts or millions of watts, it's about 3,650 megawatts of power. Like, that's a pretty big number. But of course, they don't actually save that much energy all the time, because the lamps aren't being used all the time. They're only on, let's say, 6 hours a day on average. But okay, now we can calculate an energy number. We take that 3650 megawatts times 6 hours a day times 365 days a year. And now we've got an annual energy saving number for that lighting program. And it's about 8 million megawatt hours, okay, or 8 billion kilowatt hours if you convert the units. Okay, well, how does that compare to a nuclear power plant at 1,000 megawatts running pretty much full time, about 8,000 hours a year? It's about 8 million megawatt hours. It's about one nuclear power plant running full blast equivalent that was saved in this one lighting program in Japan. And so it's just an example, but it does show the cumulative potential impact of using more efficient technologies throughout a market can actually be an alternative to very centralized energy production. And so we start to look at the different ways of using and therefore saving energy throughout our houses and our workplaces and our industries and our transportation systems. And we start to see those kinds of examples pretty widespread. So here's a chart showing the trends in the energy use and other parameters related to the humble home refrigerator freezer. Okay, now the thing about refrigerator freezers is every home has one. So there are hundreds of millions of them in use, and probably tens of millions being purchased each year. And so in this chart, the blue dots and lines show the average size of a new refrigerator sold in a given year. And you can see it's kind of gradually increased over time, but it's pretty much limited by how much space there is in a kitchen. The green line shows the average purchase price in inflation corrected dollar figures. And we can see that over time, refrigerators have actually gotten cheaper. So the consumer certainly hasn't been hurt in that way over time, even if as they've added features, ice makers, and they went from avocado green to stainless steel and all those sorts of things that happen in consumer products. But the key thing here is the red line. And the red line is the average annual electricity use in a new refrigerator sold in that year. And it went from about 2,000 back in the bad old days to it's now down below 500. So we've made refrigerators in a way that saves about 75% of the energy that they would have consumed had they continued to be as inefficient as they were back before we started making them more efficient. And the thing that drove much of that improvement was a set of policy measures, namely energy efficiency standards, which are basically regulations that say you can't sell a fridge if it's less efficient than a certain level. You can certainly make it more efficient, but you can't make it less efficient. And that started initially just in the state of California, and then gradually federal standards were promulgated, and they've gradually been tightened over the years. And there's an interesting little interval in here. If you look at, let's see if I can use the cursor here. If you look at this little flat area in the 90s, when there wasn't much improvement, well, what was going on then was that's when the need to phase out the refrigerants that were chlorofluorocarbons, the CFCs, the ozone depleting chemicals, took effect. And so the industry was under a lot of pressure to get rid of the CFCs and replace them with more benign refrigerant chemicals. And they said, hey, wait a minute, this is too much. All this regulation to phase out CFCs and energy efficiency, give us a break. So they did. They got a hiatus there to say, okay, just focus on the CFCs and we'll resume energy efficiency standards tightening later. And that's exactly what happened. They got rid of the CFCs, and a few years later started to find ways to improve efficiency further and went on their merry way. So it's kind of a success story in both the technology and the policy of energy efficiency. And if we go through the different ways that we use energy, we start to find stories like that in the past, but also future opportunities. So here's one that is more of a future opportunity, and it's particularly interesting, I think, in the Northwest, where we have a lot of buildings, houses heated with electric baseboard heating, electric resistance heating. That's a very inefficient way of using electricity, and a pretty expensive one, as you may have found if you have an electrically heated residence. And a new technology that provides a potential replacement, it's called the ductless heat pump. Well, that's kind of a mouthful, but the idea of a heat pump is it's like an air conditioner, or a refrigerator for that matter, but it runs in both directions. It can both cool like an air conditioner by moving heat from your warm space to the outdoors, or it can heat by moving energy from the cold outdoors into your space. And when it does that, it has a curious property of actually delivering more heat than the amount of energy it uses as electricity. And if that sounds like we're violating the laws of thermodynamics, I will leave it to Charlie to assure you that that's not the case. And we have, in some of our more advanced energy classes, more of a deep dive into both the theory and practice of how heat pumps work. But bottom line is it's a very high efficiency electric heating technology that has the potential to replace that bad old resistance heating in buildings, which are fairly numerous in the Northwest. And it now provides an opportunity for that electrification strategy. Remember the third pillar, because now if we replace, for example, natural gas heating with a very efficient electric technology like a ductless heat pump, you have the ability to make electric heating both zero carbon and relatively affordable because you're using so much less electricity and therefore not having to pay as much for it. So this is a very interesting component of the not only the energy efficiency pillar, but the electrification pillar of the decarbonization strategy that I talked about at the beginning. If we think about commercial buildings, we have millions and millions of these fluorescent tubes that we've been using, which are not terribly inefficient, but we can make another big leap in energy performance by replacing those lamps with LED lights, which are also easier to control and produce less heat and have better color rendition and lots of other advantages. And that's becoming just a revolution today in lighting energy design and energy use in the commercial sector. So I talked about buildings. Buildings are really important for energy use and energy efficiency, particularly electric energy. But there's also on the vehicle side. Vehicles are now the largest source of greenhouse gas emissions in states like Washington and California. And we've made some progress, and we again have the potential to make much greater future progress in energy efficiency in vehicles. This chart just summarizes the energy standards, kind of like the refrigerator standards, but this is for cars, that have been in place and are projected out into 2025 for various different countries. And you can see the US is actually kind of down at the bottom here. We had very modest energy efficiency standards, which have just over the last decade been ramped up. And we're slated to reach 50 miles per gallon by 2025, but the current administration has been trying to roll that back and has been fighting with manufacturers, states like California and Washington, environmental groups and energy efficiency advocates, et cetera, and that's still being decided. Other countries also have energy efficiency standards for vehicles. Some, like Europe and Japan, are quite a bit more ambitious than ours. Now, part of that has to do with a little different makeup of the vehicle fleet, larger vehicles in the United States, for example. But it does show that we've got some catching up to do. And again, there's plenty of technical potential to achieve greater fuel use and even an electrification strategy in vehicles. As you know, plug-in hybrid vehicles and electric vehicles are starting to enter the market. Some of them are very superior products in terms of, again, the energy service, in terms of performance, safety, reliability, et cetera. And all it really comes down to, if you want to have a carbon-free vehicle energy supply, is taking our solar output through our electrical system and charge the vehicle. And so even at the local building level, we can electrify the transportation technology and supply it with zero carbon electricity that thereby decarbonizes much faster than we can achieve that just through energy efficiency and cleaner fuels. So again, we have energy efficient and electrification opportunities across the different sectors of energy use, be they residential buildings, commercial buildings, transportation, and then also in industry. It's hard to generalize when we talk about energy use in industry, but I can say from experience, there's widespread opportunities for improving energy efficiency. When I was with Rocky Mountain Institute, we did a project with the chip manufacturer, Texas Instruments, that was debating whether to keep a new fabrication plant, a chip fab, they call it, down in Texas, or move it to Asia, where it would be a little bit cheaper to build. And our team's assignment was that if we could make it 30% more energy efficient than the baseline design, Oh, and do that without increasing the cost of building the fab, that they could keep it in Texas and justify not moving operations to Asia. And that was achieved, and improvements in all of the processes and the utilities, and everything from lighting to cooling, the machinery that makes the semiconductor wafers and chips, was successful in improving the energy efficiency and therefore lowering the cost to accomplish that goal. And you find examples like that throughout industry. So I talked mostly so far about this technology or that technology, LED lighting and ductless heat pumps and plug-in vehicles and fancy refrigerators. And technology really is the core of the idea of efficiency as a resource, using a more efficient technology rather than ever more resources to supply our cold beer and our warm showers. But I just want to remind us that every one of these actions really relies on a kind of subtle mix of not only technology innovation, which is essential, but also usually a new approach to design. For example, in that Texas chip fab, we really had to get the engineers there to rethink how they saw the problem, how they valued some of the costs and the utilities and so forth, and approach the design in a way that created a broader range of solutions, including efficient ones. It also requires new ways to look at business, new ways to look at financing things like electric vehicles, like solar panels, and also interacting with the policy regime, like those standards that we talked about. And so there's always a combination of topics that one has to get smart on when we talk about efficiency. And part of it is always technology, but the other parts are always ranging in the policy and the economic realm. And that's why in our interdisciplinary energy programs here at Western, we have every degree, even every minor, there's some mix of technical work, scientific work, but also business and policy, so that you understand the context that you're working in. One of the innovations that's been done on the business and policy side has been to try to change the business model of electric supply utilities, like our friends at Puget Sound Energy, from whom we buy electricity in Bellingham. And the idea of utilities offering energy efficiency programs to help their customers save electricity has been one of the key innovations and one of the key measures that has helped implement a lot of the energy efficiency improvements, be it those refrigerators or the heat pumps or the advanced lighting technologies over the years. And you can see that the different states that have set and achieved targets along those lines. Washington's one of the leaders. I think Vermont's probably the champion, though. They have their own dedicated energy efficiency utility, which is another kind of cool innovation that one can study on how to go about capturing the efficiency resource. You know, in the Northwest, I'll talk a little bit about the details of the role of efficiency, but we've seen the energy system go through a number of transitions in the past. And it's really an interesting context for what we're thinking about as we think to the future. And this is just a quick commercial for another one of our more advanced classes, Energy 449, Northwest Energy System Transitions. But the transitions that we look at, starting with history, are the early development of hydroelectric power throughout the Northwest and especially in the Columbia River system that from the 20s through the 70s in the previous century was really the mainstay of the development of the industrialized Northwest and everything from the World War II war effort to the aluminum and aviation industries were based on that. And of course it had a downside, particularly for native fishing grounds and the survival of the various salmon species. But it became the backbone of the Northwest economy. And then around the time in the 70s, when it looked like pretty much all the hydro that could be developed had been, the strategy emerged at the time to go into a binge of building thermal plants, namely nuclear power plants, to keep up with what was seen as ever increasing exponential demand growth. And that attempted second energy transition in the Northwest basically failed. And in the end, only one of the many planned nuclear plants was built and went into operation. And the failure of the other ones led to some of the largest bond defaults and near bankruptcies of public utilities in our history. And in response to that, the Congress passed legislation called the Northwest Power Act in 1980 that led to a new round of energy planning that became the next energy transition in the Northwest that was successful based on energy efficiency as a resource. And it was one of the first serious efforts to energy development that explicitly incorporated and even prioritized this efficiency resource that I've talked about as an element in that strategy. And that's really carried us through, and I'll show some graphs illustrating that in a second. But that's been the successful energy transition up until now. And the question today is, can we make a subsequent transition towards even more renewable power based mostly not just on hydro, building on the hydro that we have and moving to solar and wind power for the next transition to back out the remainder of the fossil fuel energy. And that's the big question. That's the transition that we're asking ourselves if we can achieve. And of course, energy efficiency would have to be a big part of that should it be successful. And that's what we're really engaged in with our work today. So this planning activity that was basically mandated by the Northwest Power Act of 1980 led to the creation of a body called the Northwest Power and Conservation Council that about every 5 or 6 years, they put out an electricity energy resource plan. And it is designed to basically keep the lights on and run the economy with the idea that it should be done at the least cost and the least environmental impact. And in order to achieve that goal, one has to consider the efficiency resource. So on the right here is the most recent plan that was published, and the council is in the middle of updating that, and will probably in the next year to 2 years publish a new plan. But what they're trying to do today is add the goal of decarbonization to retire the few remaining coal-fired power plants in the Northwest as soon as possible. And in fact, a couple of them are being retired just this year, the Boardman plant in Oregon and the Centralia plant in Washington. And as the centerpiece of the plan, they continue to pursue energy efficiency as an important resource. They continue to try to optimize and operate and compromise between power production and fish protection in the hydropower system. And they're starting to bring in more of the other renewable sources from like solar and wind and figure out how to balance those resources with the existing power resources and the demand side or efficiency resource. Now, if you look at what they've achieved with the efficiency resource to date, this chart just shows the amount of total electricity production and sales since 1980 and the additional amount that would have been needed, but wasn't because of the implementation of energy efficiency programs, energy efficiency standards, and capturing the efficiency resource. And it actually lowered the growth of electricity demand by more than half. In other words, the majority of the new electricity resource since 1980 has actually been the efficiency resource. And if we look forward, this is from that seventh power plant that was produced a couple of years ago, projecting out to 2035, they have something like 80% of the new electricity resource is the efficiency resource. And that historical amount achieved and that future projected amount achieved are each worth about 2 times the output of the Grand Coulee Dam, which is, of course, the huge hydro plant out in the middle of Washington that's the largest power plant in the whole country. So again, the efficiency resource has been the backbone of that successful energy transition from the 70s until now, and is seen as still being a big part of the future transition to ever more renewables and decarbonization of the energy economy going forward. So if we zoom back to an individual building, one of the interesting things we can think about is that combination of those pillars of combining energy efficiency with production of renewable energy right on site. And the equation here is that if you can make the building efficient enough that it will run over the course of a year on just the energy you can collect on site with the rooftop solar panels, for example, you can create what we call a net zero building, a zero net energy building. And it's actually pretty straightforward to do that for a building the size of a house. For a big commercial building, it gets harder. But I think so far the record is still the Bullitt Center, which is the headquarters of the Bullitt Foundation, led by our colleague Dennis Hayes down in Seattle. It's a 50,000 square foot, 6-story office building, and it's powered 100% by renewable energy. Now, in a net zero building, we're not going off the grid. We're producing as much energy over time as we use, but sometimes we produce more than we need, sometimes less, and we import and export, but net, it's zero over the course of the year. But it's pretty impressive that the largest net zero building so far is in sunny Seattle, right? So like, what's up, Houston? What's up, Phoenix? I mean, come on, LA. And then we can also do the same kind of thing at the residential scale. This is a nice, very modest cost design of a net zero building here in Bellingham by a builder that's active in the area. And this is this idea of designing a net zero house is actually the quarters assignment in one of our courses, Energy 360, Energy Efficiency and Carbon Neutral Design. I'll talk a little bit more about that in a minute. So one thing that occurs to people when I talk about this idea of decarbonization is it seems like it all depends on that carbon intensity of your energy supply. And if you can reduce that to zero, then you're going to have zero carbon no matter what. And so why worry about efficiency? Who cares about the amount of demand if you can meet it with 100% renewables? Well, that math is right, but that thinking is not. And the reason that efficiency is even more essential as we try to move towards decarbonization is that you just can't build renewables fast enough to keep up with demand that's growing too fast. And you've got to keep the demand within a reasonable level by improving its efficiency year after year after year. And just as we saw with the buildings, at an individual project level, you have to make the building super efficient in order to supply it with 100% renewable energy. You kind of can think about the economy the same way. And then it also comes down to cost. Efficiency resource is often very cost effective, and ever more renewables as you increase its scale and extent gets more expensive. And we can't ignore the environmental impact even of renewable resources. There's no carbon emissions, there's no air pollution, true, but the land impact and other issues, the materials that go into them, et cetera, are not trivial as we start to scale up. Sure, it's a lot cleaner on balance than the fossil fuel economy or nuclear power, but we have to be realistic about just how much power, even from renewable sources, we can tolerate. So we have seen progress. This chart shows the amount of electricity generated in the US from various sources. And you can see that just in the last 10, 15 years, there's been a big decline, finally, after all these years, in coal at the expense of renewables and natural gas-fired generation. So again, that's what raises the question that Charlie addressed right at the beginning. We're going to also have to turn that gas curve down over time. But we do see a lot of progress already. And the thing that's not obvious on this plot is what has made it possible to turn that curve for coal from growing down to rapidly shrinking as the renewables and the gas-fired generation has ramped up, is the fact that the total demand was not increasing much, if at all, over the last 10, 12 years because of our progress in energy efficiency. And that's what made it possible to not just increase renewables, but increase renewables and gas in order to reduce coal and to actually start to first ramp down those plants and now to retire them. And they're retiring at a pretty breakneck rate. And so it's the combination, not just of natural gas, but gas plus growing renewables plus steady improvement in energy efficiency that's made all that possible. So I hope that makes sense, how all that fits together: the efficiency, the clean supply, the electrification strategy as our decarbonization pillars, but the efficiency piece is really the key to making it all go, and the part that we've probably made the most progress to date, but it needs to be continued. And so that idea of efficiency as a resource, as you can see, it's been pretty important in the Northwest energy economy, in the Northwest energy industry, the utilities, the engineering companies, the consultants, the environmental groups and NGOs, and the advocates and the government agencies like the Northwest Power Council at the regional level, or the state regulatory commissions have all played a role. And so our job here at Western, with regard to preparing our graduates to enter the workforce and the professions that are involved in that whole ecosystem of energy and the clean energy transition in the Northwest, that's really kind of our mission. And so it's kind of a dual goal of trying to prepare students to be participants and indeed leaders in those fields, and then also to directly attack the climate problem and to join the clean energy transition going forward. This is just a nice picture from one of our students who graduated a couple of years and went off to a cool graduate program in, what does it say? Innovative Sustainable Energy Engineering at the technical universities in Norway and Denmark. And that picture on the right shows he and a couple of his colleagues climbing a 100-meter wind turbine tower in Denmark. So you can't say this doesn't get adventurous. But you do have to be data nerds. That's the other thing you have to say. Here's some data from Western. What's our carbon footprint look like? Well, you can see from the pie chart, it's a little out of date, but the relative amounts are probably pretty similar. Purchased electricity losses, steam plant for heating buildings. It's buildings, buildings, buildings. So if you want to reduce CO2 emissions, you reduce energy use and use cleaner fuels in your buildings. And so that's kind of the motivation for that supply, for that strategy, and also what we're trying to do on campus. So one of the approaches that we're taking is what we call campus as a lab. And the idea here is partly a really smart strategy and partly just making lemonade from the fact that the state's not about to build us a new lab building anytime in the foreseeable future. So we better make do with what we have. What we have is a bunch of old inefficient buildings, just like everywhere else in the country, that are therefore part of the energy efficiency resource as we try to improve them. And fortunately for us as faculty and as students, we have energy manager and facilities engineers on campus who are talented at doing that improvement in energy efficiency, but also ready, willing, and able to work with us as instructors and as students, and to help you all learn about energy efficiency and the potential in our own buildings, and hopefully to help them get their job done in terms of upgrading the buildings and complying with targets to improve energy efficiency. And so we have this sort of triad of the coursework, which will hopefully prepare our students to know more about energy efficiency and energy systems. We have the facilities and the buildings that need that kind of work, and the engineers who are prepared to help us achieve it. And then the student programs, the Office of Sustainability, and other sources of student interest and activism, to motivate getting those kinds of sustainability programs accomplished. So we've been running a number of projects with students, looking at ways to improve lighting energy efficiency as a start. We've assembled a tool lending library for energy efficiency measurements across campus. That's available to all the students and faculty. We've been looking at potential solar projects in the future. We put in some electric vehicle charging stations. We have a project that Professor Imran Sheikh has been running to design a zero net energy tiny house project that was meant to be installed on campus. The whole COVID situation has kind of put that in limbo, but that's another thing that we've had students involved in. And then on the kind of co-curricular side, the Institute has a Women in Energy Mentoring Network where students work with female professionals from the area in a mentoring situation to kind of learn the ropes of what they're experiencing in their professional lives, and hopefully serve as advisors and role models and so forth. And then that leads us back to the curriculum and the energy majors, minors, and concentrations that we offer, ranging from the very technical science and engineering to the policy and business-driven majors. But in each of those programs, as I said, we have a mix of technical, business, and policy work so that you can understand the context in which we're talking about energy production or the efficiency resource or what have you. This is just our catalog page for the new BS in Energy Science and Technology. We just had our first graduates last spring. Excited about that. Here's a table of all the courses by quarter. So you guys are here in Energy 101, but there's courses at various different levels on the technical side, business, policy side, throughout the academic year. There's a Business of Energy course in the spring that has, I think, only a basic econ prerequisite. That's part of our BA degree. The course that I mentioned before, Energy 360, Energy Efficiency and Carbon Neutral Design, their term project is to design a net zero house and do all the calculations and visualize it and do the economics and build physical models, the whole bit to demonstrate how they would achieve that goal of energy independence, so to say, net zero energy performance for a building. So that's a course. It's in the fall quarter, so the first chance you could take it again would be next fall. That's the contact information. Sorry, I used up all the time there, but I hope you all found that interesting and see some of the connections that we're trying to pursue. Feel free to contact me or contact Gail or talk to Charlie, and he'll refer you. And thanks for your attention. And if you do want to hang around and ask questions or just put something in the chat, that's fine too. And I'll turn off my sharing.
Thank you. Thank you.
Great. Thanks, Joel. And I'd just like to echo, if any of you are interested in pursuing a BA or a BS in energy policy or energy studies, energy sciences respectively, feel free to contact me or Gail or Joel. You can achieve that elusive dream of having a job, doing good, and making money, all at the same time.
Well, that's been kind of my motivation. I see I got a lot of questions about my cheap shot on our English friends about a warm beer and cold showers, but
yeah,
Yeah, yeah. Try to inject a little humor in the lecture there.
I have a quick question.
Go ahead.
I'm curious about what would be the next step, because winter registration is, of course, here in the next week.
Yeah.
And so what course would you recommend then?
Well, one course that you could probably take straight away is Energy 380, Energy in the Environment. Is that you, Charlie, or is that Imran in the winter?
That's Imran in the winter.
Okay, so Imran Sheikh is the instructor. I guess I would ask you if you're more interested in the kind of science and technology side or more the policy and business side. If the latter, you might want to make sure that you have Econ 206. And if you have that, you could take any of our energy econ classes. There's Energy 384, Energy 386. If you're more interested in the science side, yeah, 380 would be a good one. I wouldn't take 320 right away. What else would be a good one to take? 360 would be good, but that won't be again until next fall. Yeah, so any of those are possibilities. I would say check with Gail or me, or ask Charlie, and if he doesn't have a complete answer, he can refer you to one of us.
Awesome, thank you.
Yeah.
So I have a question.
Go ahead.
What's the deadline for signing up for these classes?
What do you mean?
Well, if I wanted to sign up for one of these classes for next quarter.
Okay, so next quarter, the registration starts, I think it starts any day now, but it's staggered by how many credits you have. So the people with the most credits, like seniors and graduate students, get to go first. And people who are just entering and have no credits go last. So the registrar has a schedule that you should be able to access in part of the Western academic calendar that'll tell you exactly what day you can register first. And so I would recommend registering then because you'll have the best chance of getting into the courses that you are your first choice. But there's no real deadline other than, you know, a few days into the actual quarter. The challenge can be if a class fills up, and that's why you want to try to register on that earliest date that the calendar allows you. But you'll have to check with that academic calendar to find out when that is. I think it'll probably be sometime next week.
Alrighty, thank you.
For most people.
Hey, Joel, do we have any businesses that we partner with the Institute for any internships or anything like that? I haven't heard anything from Gail.
Yeah, well, Gail maintains a list on the energy website, the Institute for Energy Studies website, of jobs and internships that we know about. And so when people say, hey, we've got an internship, we post it there, and you know that gets updated whenever any news comes in. So that's one source. And I mean, we don't have like a formal internship pipeline with specific employers, but they are offered by a number of the outfits that we work with, the utilities like Puget Sound Energy, Seattle City Lights, Snohomish County Public Utility District, some of the engineering firms like McKinstry, University Mechanical, Train Corporation, some of the local nonprofits like Sustainable Connections and the Opportunity Council that do energy efficiency work locally. They have internships that they offer from time to time. Sometimes they're paid, sometimes they're not, which is a consideration, of course. We've placed interns with the city of Bellingham. I don't know that there's any offer from them right now, but I continue to pester them and say, hey, how about if we go halvesies on an intern to help with, the planning work or the public works or something. So you just have to keep your eyes open, but we do post the ones that we know about on the IES website.
Okay, thank you. I might talk to Christine since she's running for
Yeah.
PUD. Yeah.
Well, she won. She won in a landslide.
Yeah, I know. She did great.
Yeah, and she'll be teaching our advanced energy policy course in the winter, the Energy 459.
I've taken that. It's a good class.
Okay.
Thank you, Joel.
Yep.
I did have a question to do with, I guess, policy, because it really ties into that whole energy efficiency you're discussing. And one of the examples I came across was actually to our local community. Is there any discussion, or is it kind of a known issue, how like the energy monopolies play a role in our ability to increase efficiency? For example, PSE, it came to my attention that I guess there's been a few cogen plants that were to be made available to use waste energy and give it back to the grid. But of course, there's kind of a conflict of interest with public utility providers because they sell energy to block that from being a thing. And so those fail because PSC doesn't want to share that business.
Yeah, I mean, that's been a problem since the beginning of what we call the regulatory compact that established utilities as regulated monopolies back in the 1930s. They do still act as monopolies. And one of the things we saw early on with renewables is that they were trying to block renewables for the same reason. And there was a law passed, it was passed in 1978, went into effect in 82, called the Public Utility Regulatory Power Act, PURPA. And what PURPA did for the first time was actually limit the utilities monopoly, or actually monopsony power, and required them under certain conditions to admit non-utility owned power sources, specifically renewables and cogeneration. But it doesn't necessarily give you carte blanche to sell power into the regulated utility systems. And there's still some places where you see proposals being blocked because the utilities have the ability to do that. Now, these days, they've actually embraced renewables, and they just, their objective is they want to own it because they can obviously earn more that way. And cogeneration continues to be complicated in most places. Usually smaller systems like under 50 megawatts is pretty doable, but large cogen facilities tend to be pretty complicated, back and forth struggles with the incumbent utilities. So there's been some reform in the direction to address the problem you're talking about, but it's not completely, smooth sailing.
Okay, it did seem on the surface like that is a place where there's room for improvement that would help with that inefficiencies, because if that could be opened up so that it opens more motivation for all kinds of sources of efficiency gains and places where we can recapture power and feed it to the grid if it's not limited to only these sources are allowed to provide power back to the grid.
Well, it's not that black and white, but there's still barriers, and that's an area of active policy engagement, as we speak. And there's different situations in different states. Just as, the energy efficiency resource is treated differently, and probably the utilities in Washington, as much as we like to gripe about them, probably do a better job of helping customers improve energy efficiency than in a lot of other places. That said, I can give you a long list of, critiques of what I think they could do to speed it up and do better. So, it's a work in progress. But there has been, over the last 30, 40 years, some measure of reform to get the utilities in particular to do a little better job on behalf of their customers to use cleaner, more efficient sources and reduce emissions and costs.
Is that a function that government has provided some incentive to do it? So for example, Puget or Cascade Gas paying to retrofit insulation, they wouldn't be doing that on their own if it weren't a government incentive to do it, would they?
That's right. Well, there's a whole kind of matrix of things that you have to do. One is to enable them to recover the cost, and that's pretty straightforward. The other thing is whether you can give them an incentive that allows them to actually make a little bit more. And that's a real slippery slope, because if you sweeten the pot too much, they're going to take you to the cleaners. And so it's a real tricky challenge of regulatory design to provide incentives to the utilities that will then give incentives to the customers to save energy in such a way that it's enough they'll get it done, but it's not so much that they're ripping off the other customers who don't participate. So yeah, the answer is yes, but with a lot of complexity trailing behind it, kind of like the previous question. You guys are asking things that are really at the crux of some of the challenges and controversies that we have to resolve.
Thank you for your time.
Thank you. Thanks for listening. Good luck with the rest of class.
No worries on my end.
That was you, plural.
Thank you, Professor Swisher.
Thanks, Charlie.
Thank you.
Oh, pleasure is all mine. Thank you, Joel. This was great, as always.
See you guys.
Hey, Aaron, did you see that podcast I linked to in the chat? Leah Stokes, she's a political scientist down at UC Santa Barbara. She just wrote a book called Short Circuiting Policy, all about power utility monopolies and why they used to be a good thing and why they're not such a good thing now. So that podcast with Chris Hayes is a
Okay, I see that.
quick look.
Yeah,
at it.
I was blown away when I heard about that locally with PSE, and it just made no sense. It's like, wait, there's companies offering to give free power back to the grids from waste, capturing waste heat. Why would that not be a good thing? Only because it doesn't benefit them financially. And I imagine that has to be a microcosm of the greater system, that happens elsewhere. But I guess that's strictly a policy thing. That's the only way to really attack that issue.
Yeah, they put up a tremendous amount of money to try to not get Christine Grant elected, because she's interested in these topics and many more, including possibly municipalizing our own power so that we can, be in charge of our own power destiny instead of relying on PSE. But yeah, it's very interesting stuff. I'm going to take off. I'm 5 minutes late for another meeting, but you all can email me if you have more questions about the energy program, because it seems like who I'm seeing on the class right now is pretty into this stuff, which is great. See you around.
Cool. Thank
Thanks,
you.
Charlie.